Steinhauer here. Welcome back. And we begin now the last chapter that we will cover in this course, chapter 29, and we'll end with a bang. This is the Big Bang. Let's think about what conditions were like at the very beginning of the universe, how we know what those conditions were like, and let's ask some of the biggest questions that can be asked. How will the universe end? What is the future history of the universe? What is the shape of the universe? What is the content of the universe? What forces are guiding the universe as a whole? That's the crux of chapter 29, and that's where we're going to end this class. Okay, let's think back to Einstein's theory of general relativity, because that is the context in which all of this stuff becomes knowable. So can we use Einstein's general relativity to model the entire universe? The answer is most assuredly yes. In fact, it was one of the first uses that it was put to try to model the shape and structure of the universe as a whole. And can we use it to predict the fate of the universe? The answer to that question is yes also. So space, we know that matter in the universe can curve space-time. We also know that space-time itself on the global scale, on the universal scale, on a cosmic scale, can also be curved. And that curvature is very important to understanding the universe. But let's first think about the matter in the universe. And we know that there is matter in the universe, and we know that that matter in the universe can affect the expansion. How is it that it will expect the expansion? We know that the universe is expanding. We know that galaxies are getting further apart. Would you expect the matter in the universe to be slowing that down or speeding it up? Well, if you know anything about how gravity works and how matter works, you know that gravity is always an attractive force, at least the way we've been thinking about it so far. And so you might expect that even though you have some separation of galaxies or separation of space or increase in the space between galaxies, gravity wants to pull those galaxies closer together. It wants to make the fabric of the universe contract back in on itself. And the more mass we have, the greater that force is going to be. Let's just say we've got a low mass density, and we begin playing our cosmic tape, and it just expands and expands and expands in a fairly linear way and doesn't really ever slow down, really. If you put more matter in the universe and begin it, you'll notice that the expansion rate's slowing down a little bit. In fact, this is very similar to, this is the average distance between galaxies, but you could imagine this as throwing an object up into the air. This one has achieved escape velocity. It's never going to come back down. But as we're not going to be throwing this thing faster and faster. We're just going to be adding more and more mass to the thing that's holding it there. The more and more mass you add to the universe, the greater the gravitational force is, the more likely it is that the universe will actually reach some large distant separation between galaxies and then begin to contract again. Let's see if we've reached that. We have. Look what just happened there. It's sort of like, again, throwing something up into the air really fast. It moves up and up and up and up. This is like its vertical position as a function of time, reaches some maximum position, and then begins to contract a bit on itself. Well, that's weird, right? Let's try that again. Reaches some maximum. Oh, it changed the mass density on me. How dare it? Take a little bit bigger than that. Going to reach some maximum separation and then start to fall back on each other. Whoa. We make it really big, it's going to happen. It's just going to happen a lot faster. Interesting. So this is important. The amount of mass in the universe must affect what the future history of the universe is going to be. Is it going to expand forever, or is it going to reach some maximum distance and then collapse back in on itself? And all of that should be dependent on what the density of the universe is right now. By the way, we're starting here because we know the universe is expanding and we know how fast it's expanding. So we know the slope here, but what happens next is entirely determined by how much matter there is in the actual universe itself. So we know that matter affects the universe. We know that if the matter is, there's too much, we know that if there's too much matter in the universe, that the universe will collapse back in on itself. We know that if there's not enough matter in the universe will continue to expand forever. Let's define omega to be the density parameter. And let's define it in terms of the critical density, the tipping point between a universe that expands forever and one that collapses back in on itself. So we can say that if the density of the universe is too high, that means that omega normalized to some critical density is greater than 1, right? That is a universe that will collapse back in on itself. If we have a universe that is too low a density, that means omega is less than 1. We have a universe that will expand forever. And if we live in the Goldilocks just right universe where omega is equal to 1, and by omega equals 1, I mean that omega, the density, the actual density of the universe is equal to the critical density. It's exactly the right amount it needs to be. Then the universe will expand and continue expanding forever, but it will stop at t equals infinity. This is the analogy of an escape of an object whose velocity is exactly equal to the escape velocity. Remember how escape velocity works. If your velocity is less than the critical velocity, the escape velocity, you'll eventually come back down. If your velocity is greater than the escape velocity, then your object will leave and never come back. And even at t equals infinity, will have some positive velocity away. If your velocity is exactly equal to the radial velocity, then yes, you will never come back down, but you will get slower and slower and slower, and you'll eventually reach velocity 0 at t equals infinity. That's sort of the just right universe. The expansion velocity of the universe reaches velocity 0, but not until t equals infinity. And so it will never actually come back down again. Okay, it turns out that these particular densities and mass density of the universe also correspond to the shape of the universe. And so the amount of density, matter density that's in the universe now, and the shape of the universe and the future history of the universe, the fate of the universe, are all intimately tied together. So the shape of the universe is something that's difficult to understand. And it's difficult to visualize too. And so just like when we're talking about the shapes of curvatures around black holes, let's imagine that the universe is two-dimensional instead of three-dimensional. And so we've got forwards and backwards, we've got left and right, but there is no up and down in this fictional two-dimensional universe. We can think about the geometry of a two-dimensional plane much easier than we can think about the geometry of three-dimensional space. So if the universe is flat, shape-wise, that means that it is a flat sheet of paper that moves off in all directions. This is the normal geometry that we think of. For instance, the vertices of a triangle add up to 180 degrees. And so if the universe is flat, that is our omega equals 1 universe. That is the critical universe. In order for the universe to be flat, omega has to be exactly the right value, exactly 0. And so the universe in this case is infinite in extent. It extends to infinity in all directions, and geometry works the normal way we think it would. Okay, if the universe is closed, this is omega greater than 1. This is our recollapsing universe. The volume of the universe is finite. So universe is finite. And spherical in shape. Again, spherical in shape, if you think about this as a two-dimensional sphere wrapped back in on itself, right? So again, this is hard to think about, but if in a two-dimensional sense, think about a two-dimensional ant on the surface of this sphere. This two-dimensional ant is confined to the surface of the sphere. And the universe is the surface of this sphere to this ant, right? And so geometry is a little bit different. The vertices of the angles of a triangle add up to more than 180 degrees instead of equal to 180 degrees. You can see how the surface of a sphere has a finite area, and it's possible that we live in a universe three-dimensional equivalent that has a finite volume. And it's weird to think about that you'd think there'd have to be an edge. If you have a universe with a finite volume, there had to be some edge. But there's no edge to the surface of this sphere, and a two-dimensional ant could simply walk around her in one direction and eventually come back to the place that she started from. We could live in a very similar three-dimensional universe. We could get in a spaceship. It's possible that if our universe is closed in this way, we could get into a spaceship, fly off in one direction, and eventually come back to the place we started from. That's a viable geometry for a three-dimensional universe. It's impossible for us to picture, but it is possible to understand it in this two-dimensional analogy. In an open universe, this is the last of the options. We have omega less than 1. This is our exceeded escape velocity and have some finite velocity at t equals infinity. And this is the another curved universe, but it's curved in the opposite direction. This is also an infinite universe, and we'll call it saddle-shaped. Here, the geometry works exactly the opposite as the spherical sense. In this case, the angles of your triangles add up to less than 180 degrees. This one also will extend in all directions for an infinite distance. So this is weird to think about, the shape of the universe as a whole, but it's intimately tied to what the geometry of the universe is, what the mass density of the universe is, and what we think the fate of the universe will be, at least in the context of how we've talked about it so far. There's more coming. So here is another diagram that shows how these universes are different. Again, we've got the omega greater than 1. This is the closed universe, the spherical universe. You see we have a beginning to the universe. The universe expands, reaches some maximum separation between galaxies, some maximum size at some future distance, at some future time, and then collapses back in on itself, and you end up with a fiery big crunch at the end. You've got the critical universe, omega equals 1. The expansion rate of the universe reaches 0 velocity, but not until an infinite amount of time has passed. And then you've got this is the flat universe. Then you've got the open universe over here, where there's not enough density. And here, the universe will slow down a bit, but it will always have an expansion velocity, and it will continue expanding in a regular way for all time. Notice something else that's interesting about these universes. Notice how far this red line here is the present. That's the now line. And it's defined by how big the universe is now, how wide it is, and also what the expansion rate is, how fast it's expanding at this particular time, which is set by the Hubble constant, which we've measured. Interestingly, in a recollapsing universe, there's less time to go back to see where the universe began. And the further you go in this direction, the further back in time you have to go to get to that point where the universe actually began, where the radius size of the universe was 0. And so each of these predicts not only a different future of the universe, it predicts a different current age of the universe, because that's really how far back you have to go to get to this point where all of these curves come together. Here's another way to look at this, a little bit easier, I think, to understand because it's a nice plot. So on the y-axis here, we've got a typical separation between galaxies in the universe. This is kind of like an expansion scale that we defined before, a typical distance between galaxies in the universe. We usually define this to be 1 at the present day. And the x-axis is time, how the universe, the size of the universe changes as time progresses. Now, you'll notice that the slope of this line is the Hubble constant, right? And we know what the slope is right now. So that sort of sets the now point. We know how big the universe is. We know what this R value is. And we know what the present slope of this is. But these 3 universes predict very different things for how the universe has evolved and how its expansion rate has changed over time. If you have an empty universe with no matter at all, then the universe, there's nothing to slow it down, and it just keeps expanding at a constant rate. And that's your omega matter equals 0. And there is your medium case, omega equals 1. Again, this is the critical universe. And then you've got your closed universe where things eventually reach a maximum distance apart and then collapse back in on itself. Interestingly, as we were seeing in the previous slide, these guys all give very different values for how old the universe is now. Because what is how old the universe is now? We know that this is the now line over here, but the age of the universe is how far back you have to go to get to a universe that is 0 in size, right? So it's that far for the closed universe, it's that far for the critical universe, and it's this far for the empty universe. All of these imply a different present age of the universe. And interestingly, we've already calculated the present age of the universe. What assumption did we make when we made that calculation? We assumed that the universe's expansion rate hasn't been changing. We assumed that it had been constant for all time and equal to what it is right now. In fact, that was the whole velocity equals distance divided by time. If you want to calculate that time, you have to assume that velocity is constant. And that is this empty universe. But we know that's wrong. We know the universe isn't empty. We know that there is matter in the universe. And so clearly, according to what we know so far, at least what we've been heard, the real universe must lie in here. It must lie younger than what we inferred by our naive assumptions of just using 1 over the Hubble constant to calculate. Okay, that's not the whole story. There's lots more to come, but that's where we are right now. So which is it? We go out and we measure the matter in the universe. What do we get? Well, there isn't much of it out there. So we get, we measure all of the normal matter in the universe, all of the stars, all of the gas, all of the dust, all the brown dwarfs and white dwarfs and everything that we can see and measure. And we get omega B, the baryonic matter, that's the normal matter, to be 0.04. Okay, that's pretty small. That's only 4% of the matter needed to close the universe, to make it critical. Great. Okay, well, we know there's a lot of dark matter out there. Maybe that can make up the difference. We add up all the dark matter we can infer. Again, we don't see any of this dark matter, but we can infer its presence by the motions of stars and galaxies and the motions of galaxies in galaxy clusters and by the gravitational lensing of more distant galaxies around. And we add up all of that and we get to about 0.23. So we get to add all of this stuff up and add the two things together, and we get a total mass density of the universe of about 0.27. Okay, so great. That's much less than 1. Obviously, we must live in a universe that is open and will expand forever and has this weird saddle-shaped geometry, right? Well, it turns out no. That is one of the great mysteries that has been solved now, though, of the 20th century. And so this is the problem. We've measured the geometry of the universe, and to very high precision, the geometry of the universe must be flat. So this is a real problem. We have a universe that only seems to contain about 27% of the matter that you need to get it to be flat. And yet when we measure the geometry of the universe, it seems, to our best measurements, way better than 70%. It seems to be perfectly flat. So there's a problem here. And we'll come back in the next video and talk about what the solution to that problem is and the new physics that we have to add that throws a monkey wrench into everything that we just talked about, but adds some new and exciting dimensions to the whole problem. Stay tuned.